Have you ever really stopped to think about what's happening inside an X-ray machine? It's this incredible blend of high-stakes physics and super precise engineering. So today, we're going to break that all down by following the journey of a single electron. It happens in the blink of an eye, but it's an amazing story. Okay, let's get into it. Everything, and I mean everything, starts right here, inside this tube. Now, it might not look like much, but this thing is the absolute heart of the X-ray machine. This is where raw electricity gets transformed into a beam of energy that can literally see through you. The big question is, how on earth does it do that? So we're going to look at this as a journey, the story of one single electron. We'll follow it from the moment it's created in a superheated wire, through a crazy high-speed collision, and see how that whole process creates a useful X-ray. And our electron's journey has to start somewhere. Before you can even think about making an X-ray, you need the raw material, right? You need a free electron. And that whole process kicks off right here, at a part of the tube called the cathode. This is it, the cathode assembly. This is the negative end of the tube. You can basically think of it as the launch pad for our electron. It's made of two critical pieces that have to work together perfectly. You've got the filament, which actually makes the electrons, and then the focusing cup, which, you guessed it, aims them. So how in the world do you get an electron to just pop out of a solid piece of metal? Well, it's a cool bit of physics called thermionic emission. The key idea here is this. If you heat a metal to a ridiculously high temperature, I mean, think of water boiling, but for metal, the electrons get so much energy, they literally boil off the surface and form this little cloud. And here you can see those two parts in action. On the left, that's the filament. It's just this tiny coil of tungsten that gets white hot to create that electron cloud. But then you've got the focusing cup. It's made of nickel, and it acts like a lens. It uses its own negative charge to kind of push those free electrons together, sculpting them into a really tight, focused beam, just like you see there. I just love that mental image. The electrons don't just pop off one by one. Nope. They form this little cloud of pure negative potential, just kind of hanging out there in the vacuum. It's sometimes called a space charge, just an invisible cloud of particles all ready to be launched. All right, so we've got our cloud of electrons. They're ready to go. Now, for step 2, the collision. We have to give them a target and a very, very compelling reason to get there. Fast. This is where the real action begins. Then, bam, a massive high-voltage circuit clicks on across the tube. And we're talking thousands and thousands of volts here. This creates this incredibly powerful magnetic field that grabs our cloud of negative electrons and just launches them across the vacuum at something pretty darn close to the speed of light. And where are they heading? They're flying towards the target. It's the positive electrode on the other side of the tube, and it's called the anode. This is the final destination, the bullseye, where all that kinetic energy is about to be unleashed in one violent, instant collision. But now, here's the real kicker. For all that incredible power and speed, this whole process is shockingly inefficient. When our electron smashes into that anode, a whopping 99% of its energy is instantly converted into nothing but pure, useless heat. That's right, less than 1%. All this amazing physics, this high-speed particle collision, it's all engineered to convert less than 1% of the energy into the useful X-rays we need. So the single biggest challenge in designing an X-ray tube isn't really making X-rays. It's figuring out what to do with the enormous amount of heat you make along the way. So how do you stop your target from literally melting into a puddle? Well, that brings us to the next step. Engineering for extreme heat. This is where we see the brilliant solutions that designers came up with to handle the fallout from that, well, cosmic level impact. And the main solution is just genius. Instead of having a stationary target, you make it a spinning disk. This is called a rotating anode. By constantly moving the target, you're spreading that intense heat from the impact over a much, much bigger area. This gives it a chance to cool down before that same spot gets hit again. Simple, but so effective. Of course, the material you make the target out of is also super important. Tungsten is the main choice for general X-rays because its melting point is incredibly high. It's often mixed with a bit of rhenium just to keep it from cracking. But for more specialized things like mammography, they might use something like molybdenum to get just the right kind of image contrast for a soft tissue. And you want to see the difference this makes? It's just staggering. Look at this. A basic stationary anode can handle maybe 15,000 heat units. But a standard rotating one, that number jumps to 500,000. A high-speed rotating anode, 1.5 million. This one change is what allows modern medicine to take powerful, repeated X-rays safely. So let's do a super quick recap of our electrons story. First, a low voltage current heats up the filament. Second, electrons boil off and form that space charge cloud. And third, a huge high voltage current fires them into the anode, where less than 1% of all that energy actually becomes an X-ray. Okay, we did it. We made an X-ray photon. But we've also created a storm of radiation and a ton of heat inside a very high voltage device. So the final piece of the puzzle is all about containing and controlling that power to make sure the X-ray is both safe and actually useful. The first layer of control is the vacuum. The whole assembly, the cathode, the anode, all of it is sealed inside a glass or metal envelope, and all the air has been pumped out. And this is absolutely critical. If there were any little gas molecules floating around in there, our electrons would just smack into them, lose all their energy, and we wouldn't get any good X-rays. Now, let's talk about the outer layer of defense. The entire vacuum tube is then put inside this heavy lead-lined metal case. And this protective housing is doing a lot more than just holding everything together. This housing is doing 3 really important jobs all at once. First off, that lead lining soaks up any stray radiation that's flying around, which protects the patient and the operator. Second, it provides electrical safety from those crazy high voltages. And third, the housing is filled with a special oil that insulates everything. And, this is key, it absorbs and carries away all that waste heat we were talking about. So when you put it all together, the vacuum, the spinning anode, the oil, the lead, all of this complex engineering has one purpose: to manage this incredibly violent process so that only a single, perfectly controlled and useful beam of X-rays can get out through a tiny window, ready to go to work. It's really an amazing journey when you think about it. You start with a little cloud of electrons boiled off a hot wire, and you end with a beam of energy that gives us a window into our own bodies. It really makes you wonder, what other invisible forces of nature are we harnessing all around us every single day without even realizing it?